Okay, let me thank also the organizers for inviting me, and in particular to the hosts here. I'm amazed by this country. It's a beautiful country, very friendly people, and I'm very happy to be here. So let me start with this very complicated title, and let's reduce it to this simplification. I want to talk about Bloch oscillations without a lattice, and if I have a little bit more time, actually, I will skip step to another topic. The main message here is that this very fascinating single particle effect that you all know, I'm sure, can turn into an even more fascinating many-body effect. See if this works. I'm too far away. Okay, before I start, let me, so this is my overview. I will talk about impurities in 1D systems, and then perhaps have some time to talk about mixing cold atoms in a very efficient way. So before I start, though, let me acknowledge the collaborators, in particular, 3 wonderful graduate students, Florian Meinert here, who's about to move to Stuttgart, and 2 other graduate students, Lukas Reichsöllner and Andreas Schinnewolf, who worked on the rubidium-cesium mixtures. So let me talk about this first, about strongly interacting impurities, and this is work that we do together with, in particular with Michael Knapp from Munich, Eugene Demler at Harvard, and Misha Svonarev in Paris. So let me digress for a second. Quantum wires, I think, at least that's what I think, are future elements in electronic circuits, yeah, in view of the ongoing miniaturization. So we see that the technology in standard electronic devices goes down into the low nanometer regime, and in particular, people are already experimenting with single atom wires here shown on the surface and looking at transport through such systems. These systems are certainly not quantum yet, but I'm confident that we, the community, will get there in due time. So one-dimensional systems are for sure special. Most of you know about this. Let me just really do the simplest on that. If you have collisions in 3D, you have the freedom for an angle. In 1D, this is not the case, yeah. So if you look at the equations for energy conservation and momentum conservation, you count the number of equations. So you see that in 1 dimensions, D is the dimensionality, you have no freedom. So that means that kinematics determines the outstates in 1 dimensions uniquely. And that has peculiar effects in conjunction then with interactions. Let's take one example that you all know. Let's talk about the interacting Fermi gas, where I introduce some Fermi momentum, as you all know. And one can look at the single particle Hall spectrum. And what you will find is that the system here, the dispersion relation, has not just this particle branch, but also it has a Hall branch. And so there are not allowed regions here, which are very peculiar. Just from these considerations, that some regions are really kinematically forbidden. Let me go a step further and generalize this. Well, I don't know if it's a generalization to the 1D Bose gas, and we'll come back to that and to some of the details. If you take the 1D Bose gas, you will actually see that you can go from the comparatively weakly interacting regime, where you have this particle branch, to a strong interacting regime, where you develop these 2 branches here. They are actually then known as the LEAP 1 and the LEAP 2 mode. And in our experiments, we can do that. We can tune interactions from weakly interacting to strong interacting with the usual tools in the cold atom physics. I'll come back to that. So this is actually a very nice system, and I will, in fact, stick to these quantum wires of bosons. In our experiments, it's an array of bosons. It's tubes that we write in the usual way with interfering lattice beams. And let me just briefly remind you of how you describe these systems. You might have seen that before. One describes this with a very simple Schrödinger equation with a kinetic energy term and a delta function interaction term. There's some parameter here, which is an interaction strength. One usually likes to write it as the interaction coupling constant in 1D, in units of the 1D density. And then written in this way, it's a dimensionless unit. It has no units, so it's a dimensionless quantity. And what happens in 1D, when you tune interactions from the weakly interacting ideal case, where you have a quasi-BEC, one will in fact go into a regime where the particles fermionize, where they build up correlations, and where they have very peculiar behavior, as I will show you in a second. Now, the parameters that I will use here are, in particular, this interaction parameter, and certainly the Fermi vector that you can introduce for any system in 1D. It's just given by pi times the 1D density. Now, how do you characterize such a strongly integrated 1D gas? Yeah, and actually this has been done now over the past more than 10 years. For example, one can measure correlations. And let me just briefly show you a couple of results from the past 10 years. This was, for example, done by Trey Porto in the NIST group, and one could look at local three-body correlations. Here's the data point, and one could see that the correlations here are strongly enhanced. A little bit later, Dave Weiss at Penn State looked at two-body correlations and actually saw that for increasing interactions, the two-body correlations are strongly, well, one usually says the correlations are suppressed, but the particles become more correlated. So actually one can also do this with three-body correlations with very strong interactions, and actually one can see that the correlations here are changed by nearly 3 orders of magnitude. So this is a local probe, yeah, and this has been done in various ways. So let's measure global properties. And in fact, one of the pioneering experiments was again done by Dave Weiss, actually before the other one that I just showed you. And this gave actually first evidence for this so-called Tongshiro gas in 1 dimensions. What they saw is a saturation of the size of the sample. Yeah. So this is a global property. What you can also do is you can measure collective oscillation frequencies. So you probe, as we just heard in various talks, you can probe, for example, the compression mode versus the dipole mode, look at the ratio. And for the non-interacting system, you would expect for the square of 4, in the mean field regime a 3, and for the fermionized regime, you would in fact expect what you know from the thermal gas, you would expect a 4. Yeah. And in fact, what that one can see in the experiment, when you tune interactions, as I will show you later, one can see that there's a striking change of the collective mode frequency ratio as one goes through from the weakly interacting regime into the strongly interacting regime, and then deeply into the strongly correlated regime. So actually one can nicely see here where the transition is from weakly to strong interaction. It happens around gamma roughly being unity. Now, just to show you that this is not some artifact, actually one can go to attractive interactions. The blue data here in this plot is for negative gamma, and actually one can see that correlations are even enhanced. That's a very, very drastic effect. So, but I will not go into the details here. This is an old story from some years back. Now, there are other methods to probe the system. Yeah? One can do Bragg spectroscopy and measure the dynamic structure factor. So let me go back to this here, to this plot that shows basically the dynamic structure factor in some grayscale as a function of momentum and energy. Basically what it measures is how can you, at a certain momentum, how well can you, and a certain energy, how well can you excite the system. Yeah? So basically what you want to do in the experiment, you want to cut through here and map out this kind of theory prediction. And in fact, this has become possible, these calculations have become possible only fairly recently, because people have developed techniques to do the numerics in one-dimensional systems at finite temperatures. Let me briefly actually look at that, because we have done experiments on this. The interesting regime, in fact, is where actually something happens. The regime where interactions are strong but not infinite. Yeah? And certainly finite temperature is also a very interesting issue. In particular, that challenges our theorists. So in the experiment, we take tubes, as I've shown you before. One plays with Feshbach resonances as a function of magnetic field, as you all know. And that allows us to tune the linear parameter from essentially 0 to very large values. Actually, I will not go into the details, but to go to very large values, actually one uses the fact that these Feshbach resonances induce so-called confinement-induced resonances. The interaction interacts with the confinement. And probing via Bragg spectroscopy means that you actually probe how much energy you transfer into the system, and that is a direct measure of the structure factor. Certainly, theory plots look very nice. So if you cut through here, through this, in this plot here, you can actually see the various branches. In particular, when it goes towards the strongly interacting regime, you see that it develops such a plateau. And ideally, in the gamma infinite limit, then you would really see like a really box-like behavior. This is, in fact, not so easily possible in the systems that we have in the experiment. We have inhomogeneous broadening. We are harmonically trapped. So actually, the data, actually, the theory data can be averaged, and so one expects, in the end, such a hump. So ideally, one would like to do these experiments in a homogeneous system, and I think at some point we will get there. So this is data of the structure factor as we increase interactions. When we increase interactions, we actually change the Fermi momentum in the system because we change the density. So one has to take that into account. This is our data. The vertical bars show where these leap 1 and leap 2 modes are. And from these data, certainly one cannot do much. One really needs the theory modeling and to compare that to theory at finite temperatures. And that's actually what we've done. And the open question, the biggest question is actually what temperatures do we have in our 1D systems? And if you look at the data, it's actually well fit by temperatures around 5 to 10 nanokelvin in most cases. Yeah, when we go to larger interactions, we have apparently a little bit of a heating, so the temperatures are not 5, but more like 10 nanokelvin. In fact, this is a nice temperature probe in retrospect. That's the way of how to measure temperature in 1D systems, strongly interacting 1D systems. But comparison with theory tells us that we really see a collective excitation, that we really excite these leap modes, in particular these leap 2 modes, which are a whole-like excitation in the system. It's a collective excitation of the system. Now, okay, but let me come to the main story. Are there other ways to characterize such a gas? Yes, there are. Actually, one can do something which we call matter wave interferometry. And you would say, well, this is not going to work. Yeah? Matter wave interferometry works only when you have no interactions or very weak interactions. Yeah? Actually, it does work. And the idea is actually shown here. If you have the ideal gas here, and then you think about when you increase interactions, you get something that looks almost like billiard balls lined up, yeah, you can say, hey, well, let's probe this kind of lining up with an impurity particle, yeah. And probing it means you actually accelerate it, you put on a force, and you want to see what happens afterwards, yeah. And in fact, this goes back to a theory proposal by Gangard and Kamenev some years ago, and who said, well, one should actually see in such a system Bloch oscillations because the lowest branch is periodic. So my naive picture is the following. If you have strong correlations in the system, you have some G2 function, and now you have an impurity particle that actually scatters off that G2 function. Yeah. I don't know if this picture is really correct. I think we need some further theory modeling here, but that's my naive picture. So let's do this, yeah? Let's do this in the experiment. But before I do so, I should really remind you of what Bloch oscillations actually mean, what Bragg scattering actually means. So if you have a BEC in the lattice, let's say, you have a band structure, and you accelerate your wave function, you get a periodic motion through the Brillouin zone with a characteristic frequency, which is set by the force and the inverse lattice spacing. So this is known as Bloch oscillation. In fact, our previous speaker and several people here in the audience, Eckhard Peik and Jakob Reichel, have shown exactly 20 years ago that this is possible to see such a behavior in cold atom systems. And in fact, I should really highlight that this has led to many endeavors in various directions. And some of the people are in the audience, and so I really was tempted yesterday to really put this in. So let me show you very nice results from almost 20 years ago from the Stanford group who looked at also Bloch oscillations and how they would Landau-Zehnach, then the atoms would Landau-Zehnach couple out of the system. So this is nothing else but Bloch oscillations. See? let me see, I'm not too quick. Then actually a group of Ennio and Arimondo saw that interactions play an effect, that when you have these Bloch oscillations with the mean field in the background, actually something happens, something interesting happens. It was done with Fermi gases by Laflorent's group, and some of the people that did this are also in the audience. Bloch oscillations were seen, actually Bloch oscillations were used for one of the most spectacular experiments, matter wave experiments, actually using cold atoms for something useful, which is actually measuring the fine structure constant. And Jerry Gabriels alluded to these experiments, actually for preparing the system for coherent acceleration by the Birabin group in Paris. This does not go as fast as I wish for some reason. Just step forward, sorry. Bloch oscillations could be looked at when you introduce interactions or you take away interactions. Yeah, one can actually see thousands of cycles of Bloch oscillations when one takes interactions away. With interactions, one can see collapse and revival effects. In fact, this was also seen by the Florence group, and some of the people who did this are also in the audience right now. Bloch oscillations were magnified into space by a little trick, by modulating at the Bloch frequency, and then one can see them in cold atom experiments. These are actually called super Bloch oscillations. One can actually then go into the Hubbard regime, where with tight transversal confinement, and look what Bloch oscillations do. They persist for very long times for non-interacting systems, and for interacting systems, they actually show collapse and revival. And finally, one can do the experiments that Markus showed earlier today, where you look at single atom Bloch oscillations in real space, and you see how the atoms sort of dephase and come back. And actually, this can also be seen for interacting atoms, here for pairs of atoms that oscillate in space and do Bloch oscillations. So the point, though, is why I showed you all this. All this work is with an imprinted lattice. Yeah, but in our work, there's no lattice. Yeah. So the question is, how does it look for the 1D gas? I showed you this kind of LEAP 2 branch here, and it turns out that when you inject an impurity into such a system, you actually also get a periodic dispersion relation. It looks like this. And the green shading is that you actually do not follow strictly this branch, but you can actually incite phonons in the system. So this is a plot where the background is infinitely strong interacting, and where the interaction with the impurity is at some finite value. And one can then actually write down a Bloch frequency. It's just the force that you apply divided by the Fermi wave vector. So can one see this? Yeah, and this is actually quite debated in the literature whether it's possible to see this. Theory says yes. This shows, as a function of time, the mean momentum that oscillates, and for stronger forcing, it oscillates at a higher frequency, but then saturates to a higher drift momentum. This is theory plots for different forces that when you like our theory friends like to normalize them in dimensionless units. They look like this, just by the actually you normalize by the Fermi wave vector squared, and then again by the Fermi vector that gives a cube. For different forcing and for different interactions, top row is 6 and bottom row is 24, one actually sees a drastic effect of Bragg reflections in a liquid, yeah? Translationally invariant liquid. The effect becomes stronger when interactions are stronger here. So one can quantify the theory a bit more. So these are the Bloch oscillations for various forcing and for various interaction strengths as plotted here. And it behaves actually as you would expect. For stronger forcing, one gets a higher frequency. One can plot the Bloch frequency as a function of the force. And one can actually look at where the value saturates out here and what the amplitude of the oscillation is in these two plots here for this ratio and for the offset B here in these plots. So I will come back to that. I just want to show you that this is possible. It's actually quite endeavor to do these calculations. In the experiment, we take these tubes and we prepare an impurity in a different spin state. We do this with a radio frequency transition from the ground state to an excited spin state. And we do this in such a way that we, in fact, do not excite the impurity locally, but we want to excite it delocalized. We want to excite a plane momentum state in the system. certainly doesn't work perfectly, but I'll show you the data later. Now, how do we tune interactions? This shows the scattering length between the different spin states as a function of magnetic field. There are two zero crossings here, and in particular, one can make the bath strongly interacting, and the impurity bath interaction is still zero or very small. Yeah. This is quantified by the 1D interaction strength, which is actually modified by tight confinement by the transversal trap frequency, and the interaction parameter is defined as before. And when I add an I to the gamma, then it's the bath impurity interaction. The scattering data is by Paul Julian. So first you do the following, you switch off interaction. So this is a situation where the bath is already quite strongly interacting, but the impurity sees almost no interactions with the bath, and what you see is essentially free fall. There's a little modification here that I don't know we don't understand, but basically we see free fall. That's good, and actually it's quite interesting. I always like this, that atoms tunnel through other atoms, yeah, and that I find it amazing. It's a very nice effect, yeah, no interactions, and we simply go through. Now, I show you data and theory comparison. The lower part is theory, the upper part is experiment, so now we turn on interactions, yeah. As I showed you in this plot, we cannot independently tune the two parameters, but we have to live with the fact that we only have one knob at this point, the magnetic field, to tune interactions. So this is now done here for various values of these two parameters. So what we do is that we successively make the bath more strongly correlated, and that the interaction with the bath becomes stronger and stronger. And I show you here the theory at the bottom part. Let me first show you what the experiment shows, that when we tune up interactions, we see that we deviate more and more from the free-falling case. Actually, in the end, you see there's nothing free-falling anymore, and you can actually see that there's sort of wiggles on our momentum distribution. So I didn't do this, and I didn't say this in detail, but what we plot here, we plot the momentum distribution in false color as a function of time. In each of these slices is one momentum distribution. To measure this momentum distribution, it's a little bit tricky, because what we do is we expand only in 1D with no interactions. So for measuring that, we actually switch off interactions abruptly, and then in time of flight measure the momentum distribution. The time of flight is not infinite. That actually leads to some initial broadening in what we measure. And also our wave packet is not a delta function initially. So one can actually quite nicely see that, that there is something happening here, that there are wiggles in this distribution. One can quantify these distributions by taking the mean momentum from these distributions and plot them for the various interaction strengths. So successively from these pictures we have strong interactions. So what we see is that initially we have the free fall, but then we deviate from that and we have two wiggles here. And then for strong interactions, this saturates to some drift velocity. And you see the stronger the interactions, it has a pronounced effect on this kind of drift because the bath really affects the impurity. I should say the theory is the green curve, and it has no free parameters. Yeah, we don't fit or anything. We just take our experimental data, put that in the theory. The theory is calculating a single tube, not an average over the tubes, but we take our average tube for the theory input, and then we really nicely fit this data. Now, from these kind of measurements, one can deduce the Bloch frequency as a function of the force. As you can see, we are in a regime where the forcing is already fairly strong. If you go back to the theory that I showed you, the oscillations are nicer if the force is not so strong. One should work in the regime of unity and less. We are in a fairly strongly forcing regime. That's simply because of the fact that the impurity is accelerated by 1/3 of gravity, and that's already quite violent. And and that what we expect from theory quite nicely agrees with our data. And one can also look at the drift momentum. These black dots are our data, and the theory is this dash, this shaded area here. And without any free parameters, it really nicely fits. This is really nice comparison with the theory results. So now, where does, there are many questions, yeah? So first of all, when you do Bloch oscillations, you know where the energy goes, yeah? You have stimulated emission, you actually eject, you redistribute photon between the lattice beams. Here we don't, so where does the energy go? Well, it has to go somewhere in the system, the energy due to the forcing, yeah? What happens for even stronger interactions? That's an open question. What happens for attractive interactions? I just showed you briefly that one can do attractive interactions. One can actually play with that, yeah? Would be very interesting to see. What happens if one now has more than one impurity in such a system and you have impurity-impurity interactions? And what happens if you actually do this with different atoms, mass imbalance system, and so on? This is totally open. It's not clear at all. In principle, now one can use this kind of technique to probe any quantum liquid, yeah? Okay, this would bring me to the second part, but I stop here because my time's up, because in fact we are working on rubidium-cesium systems where one of our goals is to in fact mix systems and to do similar things with different atoms. Okay, I will stop here, and thank you for your attention.
Thank you for a wonderful talk and sticking to the time. Questions? Yes, Martin.
Christoph, absolutely stunning data. Awesome. I wanted to ask, this is still happening in an overall harmonic potential, or
yes, very weak, extremely weak, yeah. So harmonic frequencies, the time scale is almost a factor of hundreds lower than our oscillation frequency, as our Bloch oscillation frequency.
Yeah. So would the data look any different in a box potential, or is it already in the limit where you can almost forget about it?
I think the harmonic confinement you can forget. It's mostly due to the fact that we have inhomogeneous density distribution from the loading. Yeah, because let's say the tubes in the center part are more or less homogeneous, but we have tubes in the outer part and they have different density. That's actually, I think, our biggest effect.
Yes.
So this is a very beautiful experiment. So in your experiment, how to ensure
Actually, so the question was, what about ground state versus excited bands, yeah? So actually, that's an interesting question. Certainly, our excited band in this case would be I actually have to think about it, the free particle branch. I don't think there are, in that sense, higher bands, yeah? So I have to think about it. It's actually a very interesting question, yeah? Thank you for that, yeah.
Still quite for a short question. Maybe I can put a question then. Here, when you do this with the impurities, the Bloch oscillations, you do it also with a thermal sample. And that's a real difference with the situation where you have an externally imposed periodic lattice. Can you comment on the temperature effects in this context?
Yeah, that's actually also an open question. I haven't added that. When we do these experiments, we always try to go to the lowest temperatures that we can achieve in the lab. And the temperatures are, as I showed you, that's actually also why I showed you the data, are on the order of 5 to nanokelvin in these tubes. I cannot say more, yeah? So we haven't started to look at temperature effects on this kind of behavior, yeah.
Okay, thank you. Then let's thank the speaker once again. And let's go on to the next talk by Martin Zwierlein from MIT. And the title of his presentation is Fermionic Mott Insulators Under the Microscope.